Let's elucidate matrix representations for the quantum search algorithm. We're going to treat the orthogonal superposition like a horizontal basis vector. Similarly, we're going to treat the target superposition like a vertical basis vector. We're going to use this two-dimensional orthonormal basis to construct matrix representations. The plus state is a uniform superposition of all L-qubit computational basis states. We can represent the plus state as a two-dimensional vector. The horizontal component is cosine of theta on 2, and the vertical component is sine of theta on 2. Next, let's construct some projectors. We can construct the horizontal projector by forming a ket-bra combination of the horizontal basis vector. Similarly, we can construct the vertical projector by constructing a ket-bra combination of the vertical basis vector. And that's going to give us these 2x2 matrix representations of the projectors. The horizontal projector has a 1 in the top left entry, and zeros are present in all of the other entries. The vertical projector has a 1 in the bottom right entry, and all other entries are 0. We can interpret the horizontal projector as projecting onto the non-target subspace. Similarly, we can interpret the vertical projector as projecting onto the target subspace. So we can refer to the vertical projector as the target projector. Now let's have a look at the identity operator. The identity operator can be written as a sum of the horizontal projector and the vertical projector. Or we can think of this as a non-target projector and a target projector. If we take the sum of these matrix representations, we're going to get the 2x2 identity matrix. So we have 1s along the diagonal and 0s on the non-diagonal. This is a 2x2 matrix representation, but we're not acting on a single qubit with this operator. This operator is actually acting on states that describe an L-qubit system. The dimension of the Hilbert space is 2 to the power of L, so we're specifying that in the subscript. So this is the identity operator for a Hilbert space that has a dimension of 2 to the power of L. But we are using this convenient two-dimensional orthonormal basis to construct these matrix representations. So when you see these 2x2 matrices, keep in mind that they are not acting on single qubit states. They are acting on quantum states that describe L-qubit registers. Now let's construct the matrix representation for the oracle omega. The oracle omega can be expressed as the identity operator minus 2 times the target projector. And as we saw just a moment before, we can express this identity operator as the sum of the non-target projector and the target projector. And that's going to allow us to do a cancellation. We can cancel one of these plus target projectors with one of these minus target projectors. And that's just going to leave a single copy of this minus target projector. So the oracle omega is a non-target projector minus a target projector. Or we can describe it as a horizontal projector minus a vertical projector. And the matrix representation is the same as the Pauli Z matrix. We have 1 and minus 1 along the diagonal and zeros on the off diagonal. So this may appear to be the Pauli Z matrix, but it is not the Pauli Z operator which acts on single qubit states. This oracle omega is going to act on L-qubit states, and it's going to mark the target states with a -1. When this oracle omega acts on L-qubit computational basis states that are non-targets, it's just going to give them a +1. So it's not going to do anything to them. It's the same as the identity operator acting on these states. But when the oracle omega acts on L-qubit computational basis states that are targets, then it's going to introduce this -1 phase factor. And that's how it marks the targets of search. And that's how the Oracle Omega distinguishes non-targets from targets. So now we've had a look at everything in this green box. Let's move on to the blue box. What is going on in this blue box? We're going to construct a ket-bra combination using the plus state. So the plus state that we have expressed over here in this green box, we're going to put that in a ket-bra combination. So first we're going to have this ket, and then we're going to have this bra. So that means we have a column vector followed by a row vector. And if we perform this multiplication, we're going to get a 2 by 2 matrix. And you can see that along the diagonal, we have cosine times cosine, which gives us cosine squared. And then we have sine times sine, and that gives us sine squared. And on the off diagonal, we have these mixed terms. We have the sine times cosine terms. We can use trigonometric identities to re-express these entries in this 2 by 2 matrix. So we're going to pull out a factor of 1/2 from all of these entries, and we can see that trigonometric identities allow us to shift between these different expressions. So cosine squared of half of the angle theta is the same as 1/2 times 1 plus cosine of theta. And a similar expression exists for sine squared of 1/2 the angle theta. And the only difference is that we have a minus sign in that expression for sine squared instead of cosine squared. So that explains these diagonal elements over here, these diagonal entries for this 2 by 2 matrix. What about the off-diagonal entries? Well, they come from these mixed terms. So when we have a sine of theta on 2 times cosine of theta on 2, we can re-express that as 1/2 of sine of theta. So why are we using these trigonometric identities? Well, they allow us to go from the language of 1/2 of theta into the language of theta. So we're getting rid of that factor of 1/2 inside of these trigonometric functions. So now the argument of these trigonometric functions is theta. It is no longer 1/2 of theta. And we also have this factor of 1/2 that we have factored out from all of the entries. So why are we constructing this ket-bra combination? Well, it's because it's going to show up in another definition. And it's going to show up in the definition of R. R is a reflection. And in fact, it is a reflection across the plus axis. So this plus state is going to lie along an axis in our two-dimensional geometric visualization. And what we're going to do is reflect over that axis. And the operator that is responsible for performing these reflections over the plus axis is this R over here. And this R can be expressed as a Hadamard sandwich of another operator. So here we have these multi-qubit Hadamard gates. So that's the same as applying a single Hadamard gate to all L qubits in this register. So that's what we have over here. We have a sandwich of these multi-qubit Hadamard gates. And inside the sandwich, we have 2 times a projector formed from the L qubit computational basis state labeled by all zeros, minus this identity operator. So we have 2 times this projector minus the identity, and that is inside this Hadamard sandwich. And if we bring these Hadamard operators inside, they're not going to do anything to the identity operator, but they will turn this 0 state over here into a plus state. So when this multi-qubit Hadamard acts on an L qubit computational basis state of all zeros, it turns it into a plus state. And the plus state is a uniform superposition of all L qubit computational basis states. So we're doing that for this ket, and we're also doing this for the bra. So the bra is going to come in, this bra is going to get acted on by this Hadamard, which is coming in from the right. So the ket is getting acted on from the left, and the bra is getting acted on from the right. And that gives us this combination over here. So here we can see a ket-bra combination of the plus state. And that's why we were constructing this matrix representation. And the identity operator remains unchanged because what we're doing is actually acting with a Hadamard from the left and a Hadamard from the right, and that's just going to leave us with the square of the Hadamard. So when you have the Hadamard squared, that's the same as the identity operator. And that property also works for this multi-qubit Hadamard. So these Hadamards over here, this Hadamard sandwich, is not going to have any effect. Another way of thinking of it is these Hadamards are going to undo each other. So if a Hadamard comes in from the left, it's going to cancel out the effect from the Hadamard coming in from the right. So every time we're dealing with kets, we're going to be looking at operators acting from the left, and every time we're dealing with bras, we're going to deal with operators acting from the right. So that allows us to go from this Hadamard sandwich to this more concise form. And now that we have this more concise form, we can identify two parts. We can identify the identity operator, which we have already constructed the matrix representation in the green box, and we can also identify this ket bra of the plus state, and we have the matrix representation over here. Now this factor of 2 is going to cancel with this factor of 1/2, and then we're just going to have to subtract the 1s off the diagonal, because here we have the identity matrix. So these 1s on the diagonal will disappear, and so will this factor of 1/2. And that leaves this matrix. This is the matrix representation of the operator R, which is a reflection over the plus axis. So we have cosine of theta and minus cosine of theta along the diagonal, and then we have sine of theta on the off diagonal. Now let's construct the unitary operator U. The unitary operator U can be formed by first applying the oracle omega and then applying the reflection R. The oracle omega can also be interpreted as a reflection. So in this matrix representation, we can see that we're actually negating the vertical component. So when the vertical component gets negated, that's the same as reflecting over the horizontal axis. So we're reflecting over the horizontal axis. That's what this oracle omega is doing. And this R is reflecting over the plus axis. So we actually have a composition of two reflections. And the composition of two reflections is going to give us a rotation. The unitary operator U is a rotation in a two-dimensional plane. So let's have a look at this matrix representation over here. So on the left we have R, and on the right we have omega. So because by convention, the matrix that's on the right is going to get applied first, and then we're going to apply the matrix on the left. So if we perform this 2 by 2 matrix multiplication, we're going to get this result over here. And the only difference between U and R is some minus signs. We have moved the minus sign from this cosine onto the sine. So now cosine is present on both of these diagonal terms, and then we have sine and minus sign for these off diagonal terms. So this is the matrix representation of the unitary operator U. And in the quantum search operator, in the quantum search algorithm, we're going to apply this operator U Q times. And that's going to give us a very good approximation. So we're going to turn a uniform superposition of all L-qubit computational basis states into a state that is approximately the target superposition. And we're going to do that by iteratively applying this unitary operator U. Now let's move on to the red box. We're going to see how this target amplitude amplification works. So we're going to apply the unitary operator Q times to the plus state. And let's have a look at the matrix representation. So when we apply this unitary operator U Q times, that's the same as rotating by the angle theta Q times. And that's equivalent to saying we are rotating by the angle Q times theta. So we have Q copies of the angle theta. Every time we apply this unitary operator, we rotate by the angle theta. And because we're doing this Q times, we have this factor of Q inside the argument of these trigonometric functions. And what are we applying this to? Well, we're applying it to the plus state. And just like what we saw in the green box, we have this two-dimensional vector. So this two-dimensional vector is getting acted on by this 2 by 2 matrix. And if we perform the matrix multiplication, we're going to get this result over here. So we're going to have this cosine of Q theta multiply this cosine of theta on 2. And then we're going to have minus sine of Q theta multiply sine of theta on 2. So that gives us this top entry. And for the bottom entry, we're going to have sine of Q theta times cosine of theta on 2. And then we're going to have cosine of Q theta times sine of theta on 2. We can use trigonometric identities to collapse these down into a more convenient form. So when you have cosine times cosine minus sine times sine, we're going to take these angles, we're going to take the sum of these angles, and we're going to put them inside of a cosine. So this is equivalent. This is a trigonometric identity. So here we're going to have cosine of theta times 1/2 plus q. I've just factored out the theta, which is common in both of these angles. So we're taking the sum of theta times q and theta on 2. And that's giving us the argument for this cosine. And we can do a similar thing for this vertical entry over here, this second component in the two-dimensional vector. So when you have sine times cosine, and then you have a plus over here, and you swap the cosine and the sine in this sum over here, that gives you the sine of theta times 1/2 plus q. So we're just using trigonometric identities to simplify this. And now, if we take the inner product with the orthogonal superposition, what we're going to get is cosine of theta times 1/2 plus q. And what if we take the inner product with the target superposition? Well, that's going to give us sine of theta times 1/2 plus q. So these inner products tell us the amplitudes associated with the orthogonal superposition and the target superposition. And these guys are the components in this two-dimensional vector. So we have created these matrix representations. And these matrix representations are going to help us understand a two-dimensional geometric visualization of the quantum search algorithm.